Okay, so today we are going to discuss the solutions of assignment number 4, which was rolled out in the previous year. So this is the first question of the assignment, and it asks you to figure out the current of an inductor. Current of an inductor provided a waveform of voltage is impressed on it. So this is the waveform of the voltage, and you are required to figure out the current, and these are the options which are given to you. So before discussing this question, let me discuss a thing which is much more fundamental to inductor, and the dual of it can be applicable to capacitor because inductors and capacitors are kind of a dual passive elements. So let me discuss that, right? So the relation between the voltage and the current of an inductor is given by this fundamental equation. That is, voltage is equals to L di by dt, right? So this implies that I can write this particular equation as voltage is equals to L delta I upon delta t, right? Now if delta t is tending to 0, then for voltage to have a finite value, right, will will uh, will uh, will require that delta I also tends to 0. Delta I also tends to 0 if delta t is tending to 0, right? Because then only can this ratio be of finite value, right? If delta t tends to 0 and delta I, just 1 minute, somebody is trying to join. If delta I is non-zero, right? And delta t is tending to 0, that will imply that V applied is infinite, right? Now this cannot be a practical scenario. So yeah, mathematically yes, but then practically it has to be a no, right? So in whatever situation you are seeing around you, right, the voltage has to be a gradual change uh, for any inductor application. So if you'll see this particular situation, right? This particular situation also must have a finite voltage which is being applied, which is causing a finite change in current, right? So so this situation must always be there. That is the one I just mentioned, right? The dual nature of the same is seen in a capacitor. So in a capacitor, I is equals to C dV by dt, right? So for a small change in time, that is delta t tending to 0, delta V must be tending to 0 for I to be finite, right? So the current applied in a capacitor must be finite in a practical scenario to bring about a finite change in voltage and a finite change in current, right? If you require a step change in voltage, like voltage is changing from 2 volts to, let's say, 4 volt in time delta t dt tending to 0, that means that the current must be equal to infinity to bring about this change. So this cannot be a practical scenario. So based on that, let's see what's the solution in this question number 1, and then we will go to the more detailed solution of question number 1 a little while, right? So we understand that V is equals to L di by dt, and if dt is tending to 0, delta I di must be tending to 0. That implies that I at time t is equals to 1 minus must be equal to I at time t is equals to 1 plus. Now what is 1 minus and 1 plus? 1 minus is a time instance just in the left of this 1, right? And 1 plus is a time which is in the neighborhood of just on the right hand side of this 1, right? So this is 1 plus. And let's see the solution based on this particular idea, right? So if you'll see what is the current at time t is equals to 1 minus, or you can say time t is roughly is equals to 1, right? So in this A option, it is given as 250 t square. So put t is equals to 1, you will get 250, right? Now at time t is equals to 1 plus, you will have 1 minus 1 is 0, right? And this is 0.25 t square. So t is 1, right? It will have 0.25 amperes, right? Now is 0.25 equal to 250? No. Therefore, the left hand side time t is equals to 1 minus and right hand side t is equals to t plus are not same, right? So there is a finite change in I, right? I changed from 250 to 0.25 in time delta t tending to 0. So this is not a possible scenario because this will require an infinite voltage to be applied across the inductor. But the voltage applied across the inductor is only at time t is equals to 1 minus and time t is equals to t plus, it's only 10 volts, right? The change in voltage is only 10. So this is not a practical scenario, and therefore A is definitely cannot be an option. Let us see option number B. So in option number B, the first half you will see t is equals to t minus, the current is equals to 250 amperes. At t is equals to 1 plus, 1 minus 1 is 0, 0.25 kiloamperes. Now 0.25 kiloamperes is 250 amperes. So yes, this can be a possible solution because this is 250 at 1 minus and at t is equals to 1 plus, you have again 250. So this can be a possible scenario. Okay. With that, let us go to option number C, right? So option number C is 250 t square. So again you have 250 amperes current, right? But at t is equals to t 1 plus, you have 1 minus 1 is 0, and this is minus 0.25 1 square, that is minus 0.25 ampere. So you have here 250 ampere, you have here minus 0.25 ampere. Since both are not equal, this is not a possible scenario. Let's go to option number D. So option number D is saying you have 250 amperes, right? And here if you will see, you have 1 minus 1 0.25 kiloampere, right? So you have 250 ampere and you have minus 250 ampere. So there is a change in the direction of current because the current is changing from positive to negative, which cannot happen with a finite application of voltage. So this also cannot be an option. So the only option we are left with is option number B. So option number B has to be the solution. And you can take that and just get that 1 point this question was for. So in this question, we solved this question just by inspection and from utilizing the basic principles of inductor, right? We did not do any calculation. We just saw the question, used this basic philosophy of inductor, right? And figured out the correct answer based on inspection. Which is a very good tool when you are working in a competitive examinations, right? Where time is of essence, and then you can just see the options and then kind of eliminate them based on these kinds of fundamental principles. But let's stop here for a while and try to solve this question more methodically, right? So how would you approach this particular problem, right? So you have your voltage with you, right? V is equals to L di by dt is still going to be applicable. But now what is the voltage here? So in this section, if you will see, the voltage is equals to 5 times t. So for time t belonging to 0 to 1, the voltage is equals to the voltage is equals to uh, 5 times t, right? From because 5 is the slope, right? And I have the basic equation of a straight line, y is equals to mx plus c, right? So y is nothing but voltage over here. M is the slope over here. The slope of the line is 5, and x is nothing but the x-axis is time over here, and the intercept c is nothing but 0. So you have the basic equation as v is equals to 5t, right? Now you can plug this particular equation in this particular fundamental equation, right, of an inductor, and you can write that 5t integral dt is equals to L di, right? And you can integrate it, right? Now at time t is equals to 0, current in the inductor was 0, okay? And at time is t is equals to t, you need to evaluate the current, right? So this will give you something as 5 t square by 2 is equals to I divided I into L, right? But the value of L is given to you as 10 milli Henry, right? So L is nothing but 0.01 as per the question over here, right? So the L value is given to you as 10 milli Henry. So in this equation, you have just plugged in the value of inductor, and if you solve it, you will get I is equals to 250 t square, right? So this is what is given as a solution for the first duration, 0 to time t is equals to 1, right? So you get 250 t square, but then that particular solution is given in all four, right? So you need to solve for 1 time t is equals to 1 to 2, right? Now from similar triangle, I can see that I can write that this height, let's we call it A, and this length is 2. So A by 2 must be equal to this height, let me call it height h by 1, this is 1, right? So this height h is nothing but 5, right? So A must be equal to 10, right? So from a similar triangle, right? So that is me, and since A is in the negative direction, therefore this must be cutting at minus 10, right? So the equation of this particular straight line will be equal to voltage V. The slope is going to remain the same as 5 times t, and then the c value will be given as minus 10, right? So this is the equation of the straight line for this particular time frame, right? And then you can plug this particular equation in this fundamental equation to figure out the current in this section of time, right? So then going by the same way forward, so 5t minus 10 integral dt is equals to integral I dt, right? And you can integrate it, it will come out to be the same fashion. And then like once you integrate it, you will have 5t square divided by 2 minus 10t, right? And integral sign from 0 to t, right? Here the I current, the di, so this is di into L, right? I just wrote it little wrong. So this is LDI, right? So this will become I, right? And L, again L will have the same value as 0.01, and the current at this instance 1 will be given by this particular equation, right? So this is from time t is equal like time t is equals to 1 minus to time t is equals to t, right? Or you can write here as time t is equals to t plus, because this is t plus, right? 1 plus 2 time t is equals to t, right? So and the current here will be given as the current at time t is equals to 1 plus. So 1 plus time is nothing but 250, and this current is given by I. You solve this equation, you will get this second point as your answer, right? And after that, after this methodical calculation, you can check the option number B. So you're seeing that this methodical calculation took some time, but then it is something which you must do in your free time, and then try to understand how to proceed in a more methodical manner. But in exams, you can simply use this fundamental equation, and if it is possible, just by inspection, you can approach the question and then figure out the correct solution, right? So I am hoping that this was clear to all of you, and with that, let me jump to the second question after the first question, right? Okay, so I've now moved on to the second question. The second question is stating that the voltage across the inductor is given by this particular quantity. If the current through the inductor is 0.3 amperes, find the energy stored in the inductor at time t is equals to 1 second. Okay, so energy stored in an inductor is given by half Li square, right? Uh, this is the energy stored in an inductor at any given instance of time, right? Now, here what is known to me? Here L is known to me, right? Because this is given as 2 Henry, right? So L is known to me. What is not known to me is the value of the current, right? So if I figure out the value of the current at time t is equals to 1 second, basically I will have this particular value of energy stored. So how to figure that out? Again, we have the same basic equation, V is equals to L di by dt. You have your voltage equation available with you as 21 minus e2 to the power minus t minus 2t, and you have your L. You can put that in a denominator, and you can write it as di. You can write it as di by dt, right? Or you can take the dt over here, and you can write it as integral di by dt, right? So at time t is equals to 0, current was 0. At time t is equals to t, you have your current as I, right? And then you can just solve this particular equation to figure out the rest, right? So I'm just solving it now. So 10 t in minus 10 divided by minus 2 e power minus 2t, right? Okay, and then you can just put in the limits over the here. So this will be 0 to the point of interest is 1 second, so you can just put here 1, and di will be equal to I at 1 second, I at 0 second. Now this quantity is equals to 0, so I at 1 is given by this particular equation, right? Now if you will put it here, you will have 10 minus plus, it will become minus will become plus, so 10 plus 10 e to the power minus 2, and subtraction 10t, time t is equals to 0, so this is equals to 0, and okay, something happened to my pen. Yeah, stop. No, this is going okay. So we were discussing that the equation of voltage is given to us, right? And we were discussing that you can just integrate it to figure out the value of current, right? Now the equation of the current is 10t minus 10t e raised to the power of minus 2t, and the limits were 0 to 1. Once you put in this limit, you can have the value of current at time t is equals to 1, right? So there is nothing in this. You have just solved this particular equation, right? Integral equation, and you have come with this final solution. Now you need to substitute in the values of these limits. Once you substitute in the values of these limits, you will have the value of I is equals at I current I at time t is equals to 1. Uh, I'm hoping it's clear to you. And once you have the current at I time t is equals to 1, what you need to do is you need to write just that energy is equals to half Li square where the current is given by current at time t is equals to 1, right? So you substitute in this particular value, right? And then you try to solve it, you will get that correct answer, right? And based on that, the answer will come out to be between 35 to 37 joules. So that will give you the correct answer as option number D. So try to just solve it and then let me know in the next class if you are getting the solution number D as the correct answer, right? So let me move on to the next question, which is very important. It's related to figuring out the solution of a RC network, right? Okay, it's not the solution. It is just the figuring out the equivalent capacitance. So this is a very straightforward question then. So all capacitance are of 4 microfarad, right? 4 microfarad, 4. So if you see these two capacitance, these two are coming in series, and therefore the effective capacitance will be C by 2, right? Because both are of C value. So it will become 2 microfarad. And 2 microfarad is coming in parallel with this. So these two are in parallel. So 2 microfarad and 4 microfarad parallel is 6, right? Similarly, since this is symmetrical, you can write the value of capacitance as 6 microfarad for this particular section, right? And if you'll see, these three sections are coming in series with the one in the center, right? So this is 6 microfarad from this section, total 6 microfarad. And the central section is 4 microfarad, and the right section is again 6 microfarad. So, and you have to figure out the capacitance between these two. So this is 4 and 4 will give you 8. So finally you have 6 microfarad in parallel with 8 microfarad in parallel with 6 microfarad. If you will try to solve them, you will get the final answer, and that final answer is going to be sorry. This is not in parallel. This symbol is wrong. So 6 microfarad in series with 8 microfarad. 8 microfarad, right, in series with 6 microfarad. So this 4 and 4 was in parallel, and therefore it is 8, right? And 6 microfarad is coming in series with 8 microfarad. 8 microfarad is coming in series with 6 microfarad. So you can try to solve them and you will get the final answer, right? So it will be nothing but 1 by 6 plus 1 by 8 plus 1 by 6 inverse, right? And this will give you the final answer as 2 point something, right? And that is your final answer. So this is straightforward, but I think the next question is going to be a little more interesting. So the next question is stating that you have to figure out the value of R, which will make the energy stored in the capacitor the same as the energy stored in the inductor, right? Under DC state operations. So what is the energy stored in an inductor first of all? So energy stored in an inductor is half Li square, okay, as we had seen previously. What is the energy stored in a capacitor? It is half CV square. What is the voltage? Voltage is the voltage across the capacitor, right? So this is plus and minus, so delta V is the voltage across the capacitor. This voltage will be going here, right? And what is I? Current. This is the current which is flowing in the inductor, right? So you figure out the current flowing in the inductor, and this will give you the current expression in this particular energy equation. Okay. Now, what is the what is the state of the of the inductor in when steady states will come? So in steady state, the when DC current is applied in it, right, in this particular section, it will have some finite voltage in it, and it will behave as an open circuit. So in DC state operation, you can just finalize this like the effective network as something like this. Current R, this will be an open circuit, and inductor will be behaving as a short in the final steady state operation, right? So this will be behaving as a short, and you have this particular network with you, right? So now what you need to figure out is that the value of R, which will make these two expression same, right? So according to question, 1 by 2 Li square must be equal to 1 by 2 CV square, right, as per the equation. So this implies that 15 millihenry current, and the current which is going in this particular branch, same current must be coming here, right? Current going in this branch must be coming over here, right? Because this is an open circuit, so current cannot go here, current has to come here. So current I square, right, from this equation is equals to C, capacitance C, 160 10 power 6 because microfarad, right? V square, what is the voltage across the capacitance? It is nothing but IR drop, whatever the IR drop was here. So IR square, right? So I square also will be cancelled. You are left with R square is equals to 15 0.015 divided by 160 into 10 power minus 6, and this is R square, so R will be equal to square root of this quantity. So you try to solve this particular square root quantity, and then you will get the answer. I don't remember very clearly what was the value of R, so just let me try to see it in the question set which was given to you. Okay, the value of R will come out to be accepted answer A, somewhere between 9.5 and 9.8, right? So if you solve this particular square root, right, in a calculator, you will get option number A. So what are the two things which you learned in this particular question? The two things which you learned here is that in steady state operation, the inductor is a short circuit, right? Inductor does not give you any resistance, so it is a short circuit to a DC current, right? And capacitor is an open circuit, right? So no current will flow through it, so it will just be an open circuit, and this is the two information you derived out of it. And then after that, everything was there in the question. It was asking you to equate the energy and then figure out the resistance. So that is what you have done. So I'm hoping that the two principles are clear to you. Okay. And if they are clear to you, it's great. But if it's not, please feel free to respond. So I'm hoping it's clear, or if it's unclear, please question me. Okay, great. So now there is a fifth question, right, which is asking you to figure out the time constant, right, of the circuit. So let's try to address this question. So this is 2 farad. Okay, 2 farad and 2 farad are coming in parallel, so this will become 4 farad. And 4 farad is coming in series with 2 farad, so this is 4 into 2 divided by 4 plus 2. So it is 8 by 6 or 4 by 3. So this is the effective value of capacitance, right? So now it is 4 by 3 and resistance is 3 ohm. Resistance is 3 ohm and current is 6 ampere. So this is the like the same circuit as the first one, only a little in a reduced form, right? So if we need to figure out the time constant of the circuit, the easier method can be, okay, uh, you have this particular capacitance, you have R over here split like this, right? So I can use Thevenin's theorem and then I can figure out what is the effective R Thevenin when you are looking from this particular end, right? So R Thevenin will be given as R Thevenin will be given as uh, you have this particular circuit, so R Thevenin at this particular instance will be given as just give me a minute. So you can open up the open up this uh, what do you call it? This what is this? This current source, right? So the current source will be open circuited, and you will have circuit in the effective form as 3 ohm, right? And this is 3 ohm, right? And you will have something of this value, right? 4 by 3 farad. And you are now required to find in the R Thevenin looking at from this particular port. So this is one possibility, right? So you find out the R Thevenin using this. So when you are figuring out the resistance, this capacitance will be serving as an open circuit, right? Because when you're figuring out the resistance, the capacitance, it implies that you are taking the resistance in DC state, and therefore the capacitance will be replaced by an open circuit. So if this capacitance in an open circuit, then the only resistance which is going to come into picture is this particular resistance, right? So R Thevenin is nothing but this particular resistance. So RTH is 3. And the VTH is going to be given as the VTH is going to be given as current 6 ampere into the 3 ohm resistance, right? So this is going to be the VTH. Now you have the VTH with you, you have the RTH with you, you have the effective capacitance with you. You can figure out the RC time constant, right? So this is one method of doing it. But let us approach this question from a little more fundamental way, right? So let me just try to solve that in a more fundamental way, right? Okay. So we had taken current as current I, right? Let me take it as more general situation. So you have a resistance over here. You have R1, let me call it R1. You have R2 over here. You have a capacitance over here, right? And you are required to figure out the RC time constant of this, right? So let me just take it the potential as potential V, right? And let me write the node equation at this point. So it will be given as the current I is equals to voltage divided by resistance R1 plus the current over here as I2, right? But what is I2? I2 is equal to C dV by dt. Let me call it dV2 by dt. So what is V2? V2 is the potential across this, right? But what is V2? V2 is C D voltage V minus I2 into R2 dt. Correct? Because this is the drop in this particular resistance which is coming as V2, right? So you can just substitute this particular thing over here, and this will become I V divided by R1 plus C, and this is dV over dt, right? And this is nothing but C into R2 di2 by dt. I've just substituted it and expanded it now, right? Now what is I2? I2 is nothing but I, constant I, minus V divided by R1, correct? So I can further write this particular expression as current I, or capital current I, is nothing but V divided by R1 plus C dV by dt minus C R2, and taking a derivative of di2 by dt is nothing but taking a derivative of this quantity. So constant is 0, and you will be left with dV by dt divided by R1, and since this is minus, so minus minus will become plus. So this is the final equation. Now you are left with a single order differential equation in voltage, right, which is easy to solve. So you can write here as I minus V divided by R1 is equals to dV by dt, and this will become C R1 plus C R2 divided by R1. This is the quantity, right? So you can further simplify it to be this. You can write it as is equals to I R1 minus V divided by R1, correct? So R1 and R1 is cancelled, and you are left with this quantity. So you are left with dV integral IR minus V is equals to dt over C R1 plus R2, correct? Okay, and this is integral, right? From where to where? From 0 to time t, and from where to where? From 0 to voltage V. So if you'll see this particular integral, this is nothing but ln IR minus V with a negative sign, right? From where to where? 0 to voltage V. So you can write it as, so if once you will put this particular quantity inside it, it will become ln first the negative will swap the limit, so it will become ln IR over, or you can keep the negative sign outside, because I want to take because I have something in mind which will come in the future. So you can keep the minus sign outside. So it will be ln I over this divided by IR, right? And the minus sign will be there, will be equal to time t, dt integral is time t, t upon R1 plus R2 into C, right? R1 plus R2 into C, and you can write from here that the voltage is nothing but equal to IR 1 minus e to the power minus t R1 plus R2 into C, right? So you can see here that R1 plus R2 into C is the time constant which is there for this particular circuit, right? And this is going to form the equation which is going to give you the solution of the question which was asked here. So here also you have the same situation, like you have effective value of capacitance, you have R1 and R2, and the solution of the generalized solution we have figured over here, right? So the generalized solution is nothing but R1 plus R2 into time constant, into C is the time constant from this particular equation. So you can put this in this you can put the values of R1 and R2 and the capacitance, which is the equivalent capacitance, in the solution we have derived, and from that you can get the value of time constant. So Thevenin's and all these things are possible if you have some simple circuit as was there in the present case. But if you have something much more tricky, then you will have to resort to more fundamental equations as was derived over in this slide, right? You write the basic equation of Kirchhoff or the nodal equation, and then you try to figure out the value of time constant from that particular thing, right? So this is the solution. This is how you are going to approach this particular problem, and this will give you the final solution as we have seen till now. It's equal to R1 plus R2 into C is the time constant, right? This is what we had deduced over there. So if you'll just plug in the value of R1 and R2, so this is 3 plus 3, and the C value is C effective, right? So C effective we have calculated over here. So C effective is 4 by 3. So this will give you 6 into 4 by 3. This will give you 8. So so you solve this particular equation to get the value of RC as 8 seconds, because this is in farad and this is in ohms, so the time has to be in seconds. So 8 seconds is the time constant, and which is the option number D, and thus you get the answer, right? So I'm hoping that this fifth question was also clear to you guys. We have run out of time. So you see the recording of this particular lecture. If you have any queries, right, please let me know in the next class. So I'll wind up this particular session now. I'll request you guys to move to the next room in which my colleague will be taking the class